Today I'm talking about LeetCode problem 63, unique paths. What this problem asks you to do, it's similar to the previous LeetCode problems, unique paths 1. What it asks you to do is it says it's going to give you a grid, and the grid can have obstacles on it. An obstacle is going to be marked by a 1 in the grid, and a space that you can walk on is marked as 0. And you control this robot starting at the start position. And what you want to do is find the number of paths that can reach the end position, the number of different paths that can reach the end position without traveling through the obstacles, obviously. So I drew this little diagram because I thought that this was going to work the same way as unique paths 1 as the original, and in fact it does. So what I do here is I say, okay, the end is 1. If you're at the end, then you have one path to the end. And then our robot, I forget if I mentioned this or not, our robot can only move down and right. So if you're at the end, you can only reach the end from above it by going down, or to the left of it by going right. And yeah, so then what you need to do is set the value for the adjacent cells to be the sum of all of their adjacent values. In other words, from this cell that I'm currently drawing around, you can reach the end by going right or down. So you take the sum of the path on the right plus the sum of the path going down, and that's 2. And then you can fill in the other cells similarly. So I'll just quickly draw this. End, start, 1, 1, 2. I guess I don't really need to fill it in. 1, you can only go down. 3, and 2. Excuse me, this one's 3. And here we are at 6. So what makes this problem different than the previous unique paths 1 is that we can have these obstacles, spaces we can't move through. And so how I treat those is I just say that there are 0 paths going through the obstacle that reach the end. So rather than follow the behavior for a normal square where I'd sum the paths down and to the right, I just say if it's an obstacle, then it has a value of 0. It has 0 paths that go through it to reach the end. And so with this approach, we can essentially solve the problem. And if we're ever in the special case where, say, all paths are blocked, then this will work as is. So start, end, if we have blocks all around, then these just go to 0, and everything else is 0, proceeding out from it. So 0 paths to the end if it's blocked. I think that makes sense. Yeah, so how this is going to work, the function that the solution object is required to have is this unique paths with obstacles function, and it takes the obstacle grid, and the grid is that a 2-dimensional grid, or a list of lists, 0 being a traversable space and 1 being an impassable space. And what I'm going to do is I'm just going to call my helper function robot at, which I'll explain right now. So robot at is going to approach this in a recursive way. It's going to have a base case as the first thing, which says if the Rx or robot's X position or the robot's Y position is outside of the bounds of our grid, so if the robot has traveled off the edge of the grid, then we're just going to return a 0. Just return a 0. The next thing we do is construct this args tuple, which I'm going to use for memoization. I'm just going to store the request, any unique request, in a dictionary that's specific to my solution object. So if you've ever tried to get the number of paths from a coordinate before, rather than calculating it, we'll just be able to look it up in our robot ats dictionary. So once I have the tuple, and I should say the reason for using a tuple is because I just want an easy way to look up these two values in the robot ats dictionary. So here's the check that I was just describing. If the args are in my robot ats dictionary, then just go ahead and return the answer from the robot ats dictionary. The robot ats dictionary is just where I collect previous executions of this function. So if I have an execution with the same input, then I know what the answer is without having to do any calculation. Another base case would be that there's an obstacle at the position you're currently looking at. And in this case, we're just returning 0. This is what I was saying with the red X. There's an obstacle if we're evaluating this position, so just return 0. So if the robot's X coordinate is equal to the last space on the grid, so the length of the grid less 1, or I guess I see. Sorry. And the robot's Y coordinate is equal to the length of the X sublist of the grid, meaning we would be down here. So we're at the maximum X and the maximum Y. Then we're at the very end and we can just return 1. So if we're evaluating the final spot, we can return 1. So those are the base cases. We already have the answer, we're off the edge of the grid, it's impassable, or we are at the end. So what we do is we just say, okay, let's say the right value is going to be my recursive case. We're going to call the robot at function, pushing our robot 1 to the right. The down variable is going to get the value of the recursive case, pushing the robot 1 down, adding 1 to my robot y. And then the result is just going to be the sum of the right and down paths. And then we're going to store the result in my robot ats dictionary so that we can look it up if we need to a second time. And so that's essentially the code, and it winds up running pretty fast. When I ran it previously, it's faster than 99.2% of other Python 3 submissions. I don't know how many Python 3 submissions there are. You can see I was tinkering with it for a little while to try to get the solutions, or try to get it to run faster by just taking things out of the solution and then rerunning it. And eventually it got to be pretty quick. But that's the solution. I'm going to try to do a LeetCode problem a day, maybe slightly more frequent than that. So if you're interested, like the video, comment, let me know you're watching, or subscribe to see more LeetCode problems. Thanks a lot for watching. Bye-bye.